আজকে তোমরা 13 জন হলে, 9:21 বাজে, এখনো যা দেখছি সব মিলিয়ে তোমরা 13 জন এসছো। কি করবো বলো? 13 জন, 45 জনের মধ্যে না কত জনের মধ্যে জানো? 47 না 46 জনের মধ্যে 13 জন এসছো। ক্লাস স্টার্ট করবো? হ্যাঁ কি না?
হ্যাঁ ম্যাম, করে দিন।
ওকে, ঠিক আছে। স্ক্রিনটা শেয়ার হলে একটু বলো। হয়েছে?
হ্যাঁ ম্যাম।
ওকে। So today we are going to discuss about memory, as in memory in broad sense. Until now we have seen that how to store maybe a 1 bit, 2, 3, 4 bits in the form of flip-flops, and then when the flip-flops are connected in such in a particular way we can form certain registers. So we have seen that. But in computer system we don't really deal with just 1 bit, 2 bit or 4 bit at a time. We deal with a lot of bits at a time. The word length is much more in case of computer science. Maybe it is of 32-bit length, of 16-bit length, maybe more than that. So for that we need a permanent memory system to store and to deal with this. So basically what is memory? Memory is nothing but something that memorizes or something that stores. Now what are we storing? We are storing either some data or a program. Program means obviously some sequence of instructions, and since we are dealing with digital electronics and computer understands only zeros and ones, so the entire program is written in a coded form. What is the coded form? Nothing but the pattern of zeros and ones. So a memory element or a memory unit that store information, data and programs. Now what is a memory unit? Memory unit, a single memory unit actually contains a lot of memory cells. It can contain maybe 8 memory cells altogether, 16 memory cells altogether, but it is situated in one memory location. That can be done. So in this particular chart you can see a classification of memory. So a memory is classified into these 3 types of categories. One is obviously semiconductor memory, another one is optical disk type memory, and then magnetic tape or disk type memory. So in case of magnetic tape or disk, here actually the magnetic property of the particular material is exploited in order to store something. And here the access time is large, or we can say that for magnetic tape or magnetic disk the access time is largest among these three types of memory. Then we are very much familiar with this optical disk memory. Here the light property has been exploited, whether it is getting reflected or whether it is diffracted from the surface. Depending on that, the data are stored. There are certain advantages of this optical disk type memory. Obviously it has got, one of them is large storage capacity, it is of low cost, dust immune, and access time is almost comparable to hard disk. Now some optical ROM, CD-ROM, write once ROM, these are coming under this optical disk memory, but in this present course we are not going to see details of these two types memory. We are jumping to the third type of memory, that is what we call as the semiconductor memory. Now why semiconductor memory? Semiconductor memory, here a semiconductor device is utilized to build up these memories, that is why it is termed as semiconductor memory. And the main advantage of using this kind of memory is it is fastest. It is faster than magnetic tape type, it is faster than optical disk type memory. So we, in present VLSI technology, we with the device scaling, we can scale down each device to increase the package density. Also, we take care of the thing that it must consume the low power, so that it can operate under low power supply voltage. So all these merits, we actually try to build a memory utilizing those semiconductor devices. So basically it is fastest. Now there are two types of memory. You are very much familiar with these two names. One is RAM, another one is ROM. What is the abbreviation of RAM? RAM means random access memory. And what is the abbreviation of ROM? It is read only memory. Now from the name random accessory memory, why is it called random accessory memory? Not accessory, random access memory. Why it is called that? The main reason is that what we do with a memory cell, either we write something into the memory or store something into the memory, or we retrieve data from the memory. So either we write or we read. Now this write and read, it needs some time to complete that entire operation. That time is actually independent of the physical location of this memory in the memory unit. So it is independent of the physical location of that particular memory cell. We can actually access randomly. It doesn't mean that if I have written to a memory location particularly at first, that means we least access time is needed there. No, it is nothing like that. You can store the data in any sequence you want, but while retrieving the data, the time will be same in all the cases. So that is why the name random access memory. And this is a type of memory where you can easily write as well as read from this memory. So alternatively, it can be termed as read write memory or RWM. Now what is ROM? From read only memory, you can easily say that it is something of a memory that we can only read from this memory. It is very difficult to write or alter this memory. We can write or we can alter, but it needs a lot of processing. So the name read only memory is given to this particular memory segment. Now the thing is the access time dependent on the physical location of memory unit or the physical location of memory cell in this ROM? The answer is no. Here also the access time is independent of the physical location of this ROM, physical location of the memory cell. So this ROM is also random access memory. Now it would have been more correct if this RAM name, instead of giving RAM name to this part of memory, we give read write memory, that is RWM, and here it is given ROM, because both of them basically are random access memory type. But it is due to the technical jargon, the name read-only memory is given to this particular memory where we can from which we can read only, and the read-write memory is named as RAM or random access memory. Another difference between this RAM and this ROM is this one is volatile and ROM is a non-volatile memory that is more permanent. Now, what do we mean by volatile? Volatile means as long as the supply is on or the power supply is on, we can read from RAM and we can write into RAM. As soon as we switch off the power supply, whatever data is within the RAM got erased or got vanished. So, in that sense, this RAM is volatile. On the other hand, the ROM, whichever program, once it is stored in the ROM, it stays in it. Whether you switch on the supply or you don't. When you are switching on the supply, you don't have to load the program or load the data again. You don't have to do that. It is already there. You can easily access those programs or those data from read-only memory. It doesn't vanish. So these are the two main difference of this RAM and ROM. Now, if I give a very real time example, in the computer or in the mobile that you use nowadays, both have got RAM as well as ROM. And we often say if you are doing any multitasking, then obviously we need more RAM. ROM means maybe the internal storage. It might happen that suppose you have got an internal storage of 128 GB, but one variant of mobile is coming in 6 GB RAM and other mobile is coming with 8 GB RAM, then the multitasker will definitely go for the 128 GB internal storage with 8 GB RAM. It is also said that the RAM makes the device work faster. Now why? Basically what RAM does, when the system is powered on and suppose you want to call 2 or 3 applications at a time. Suppose you are doing a work in Microsoft Word. Also, you are watching some videos on YouTube. Also, you are doing some work on the Excel sheet. So 3 works you are doing at a time. Now to execute those 3 applications, you need certain programs to be called for, and those programs that are already stored in ROM, now you are calling that from internal storage, not all of them, but only the portion that is needed to perform that particular task that you are doing. So that portion of program is now loaded into RAM. So basically you can think of RAM as a kitchen table, while internal storage is the refrigerator or maybe the kitchen storage. So when you are preparing something, suppose you need to prepare a particular dish. For that you need to you need to chop some vegetables. You need to maybe arrange all those vegetables on the table at first. Then you need a chopping board, a knife, and then you need to perform the task. So to fit all those ingredients, the table size, the more the table size, the more you can actually arrange different items there. Maybe you are going to prepare two dishes together. So ingredients of one dish you can arrange on the table, and ingredient of the second dish you can also arrange on the table. So here the RAM is large, the table size is large. But if the table size is small, you are restricted to you're restricted to make only one dish at a time, because you don't have any place to keep the ingredients for the second dish. So basically that is what RAM does. If RAM is large, from maybe 8 GB, it can actually access all 3 programs that are needed to execute those 3 applications separately at a time. But if RAM size is smaller, suppose you have got 2 GB RAM, then maybe you could run one game at a time, but you cannot access any other applications. Or maybe you are coding. Suppose you are writing a program in C, or maybe in Java you need the windows to appear side by side, but for using for writing C you are using Turbo C, and for writing Java maybe you are using Eclipse. So those two programs you need to run simultaneously, because once you are coding here also here, so you need to see those programs and the running, and you want to see both the outputs at a time. For that, you need required amount of RAM. In both the cases, internal storage may be 128 GB and that is sufficient, maybe. But depending on RAM, it will depend that whether your system will run smoothly or it will crash. So that is the basic difference between RAM and ROM. So both of them has got its own significance. And now, why it is volatile? Why do we need a volatile piece of memory if it is not storing the data permanently? Then what is the use? That is the use, because after the completion of the program, after you switching off that particular application, you don't need those data to linger in that memory. You need that to be erased. So that can be done. So when you are switching off your mobile or you are switching off your computer, then obviously you want that portion of memory to be clean, so that when you again switch on the computer, maybe you don't want them to run Eclipse and Java, maybe you then want to run some game, or maybe you want to work on Microsoft Office. So depending on that, you will always get a clean slate in the form of RAM. So that is the significance of RAM being volatile. And obviously you need some programs to store permanently, because to um, the Eclipse or maybe the Turbo C, whatever be the application, some executable file, not executable file, some programs must be there that ensures that the application could run smoothly. So that is stored in ROM. Now these two both are random access type memory. Apart from these two, there are another type of memory, that is what we call as sequential memory. Sequential memory. Here, the access time is actually depending on the physical location of the particular memory cell. Suppose, so it is a kind of fast in fast out technology. The data you are stored to a particular memory location first. You minimum time you need to you require minimum time to access that particular data. And this type of memory, obviously the access time is variable and access time is large. So this type of memory is not preferable where you randomly need to read and write data, or where you frequently rather need to access this memory. So generally, operating system of computer is stored in this sequential memory type. So when you switch on, the boot screen comes up and the booting happens, that only happens once. So you can actually wait for like 1 minute or 2 minutes. So generally the operating system is for storing that, the sequential memory has been used. Now let us come back to this RAM and ROM. We are going to focus on these two. Both of them can be built using BJTs or MOSFET. Both are semiconductor devices. So you see, RAM, we can use BJT to make RAM. We can use MOSFET to build RAM. Also in case of ROM, we can use BJT, we can use MOSFET, and we can also use diode. But that is nowadays, diodes are not used, so that is why it is not written over here. Now, there are two types of RAM. One is static, one is dynamic. Dynamic and static RAM. In dynamic RAM, actually the surface area or the circuital component that we need is very less compared to the static RAM. So that actually buffs up the package density. But in case of static RAM, although we require more area and we require more number of transistors, that is more circuitry element, but we don't need to refresh it time to time. But in case of dynamic RAM, we need to refresh it time to time. A typical DRAM needs to be refreshed in every 1 or 2 milliseconds. So that is a kind of hazards. But we can form the simplest form of DRAM or dynamic RAM by using one NMOS and one capacitor. That is not possible in case of static RAM. We need definitely a lot more transistors than that just one transistor. So these two are there, and with BJT we can only form or we can only design the static RAM. In case of ROM, with BJT we can use the static ROM, but here we are more interested in the MOSFET based ROM. It can be mask programmable, erasable programmable ROM, that is EEPROM, or programmable ROM, that is PROM. And in this erasable programmable ROM, there are two types. One is electrically erasable, another one is electrically alterable. So one is E square PROM, another one is EA PROM. We will see that, but mainly we will focus on PLA or PLD. So this is the total summary in the nutshell, that what is memory, what type of memory we want to study, and what type of memory nowadays are used, and so on. Now a little bit of history if you want to know. Basically, the first RAM using MOS technology, it was reported in 1960s in a conference that is called the International Solid State Circuits Conference. International Solid State Circuit Conference. It was first reported, and commercially it was available in 1974. Now, why this MOS technology is preferred over BJTs? Because of two reasons. One is due to its low power consumption, and another advantage of this MOS transistor is it can lead to high packing density or high package density. These two are the reasons why MOS based RAM or MOS based ROM are preferred over BJT based RAM or BJT based ROM. So, before going into the detailed circuitry of RAM, let us talk about the organization of static read-write memory or the static ROM. What would be the components? What we need to do? Here there are three components are given. One is address lines, then data lines, then control input. So what do we need these address lines for? Address lines means some data bus through which the address is flowing. What do we mean by address? Address actually denotes the particular location of a memory cell, that is which memory cell is needed to be activated in order to read from or write into. So those lines that carries the address bits, these are called address lines. Now what is data lines? Obviously from this term you can say that the lines through which the data is traveling, either the retrieved data or the data which is to be written in that particular memory cell. And then comes control input. Why do we need these control inputs? There are three types. One is CS, another one is WE, another one is OE. What are these? CA stands for select. It basically selects a particular chip. Which chip is pointed by the address bit? Suppose I am giving 00. 00 is pointing a particular memory location, and in that memory location, suppose there is a group of memory cells sitting. So we need to enable those memory cells in order to write in those memory cells or in order to retrieve the data from those memory cells. That particular thing is done by enabling this chip select control. Now this chip select control can be active high or active low, depending on the system you are designing. Another one is WE. What is WE? WE stands for write enable. When you want to write something in that particular cell, you need to enable this particular control so that it goes to write mode and you are able to write the data in this. Here it is also, it can be active high or active low. And this one is OE, output enabled. Output enabled means basically when we are reading from that cell, that is output are enabled to get in touch with the data bus, through which the data which we want to read flows and becomes available at the data output pin. So that is the significance of this third control. So now if we come down to this particular diagram, this is a block diagram of this entire thing. See here, one is control logic with CS and WR given over here. This one is the memory cell array, or alternatively we can call that this is a memory unit containing multiple memory cells within it. These are the data buses. These are the data buses, input and output. Here in this particular direction, we can see that the output data bus is fed back to be connected with the input data bus. And these four in the input and these four in the output, they are nothing but the tri-state buffers that we have already introduced in the previous classes. So here what is happening? Here the address bus is actually not shown. Basically, this is a common IO data bus. At one point of time, this tri-state buffer remains inactive and this tri-state buffer at the input remains active. When this tri-state buffer remains active, then the input data can flow from here to here. That is, we can actually store the data from this through this data bus. In that case, this data bus is acting like the input database. And in other instance, this tri-state buffer is active while this is inactive. That means when this is active, it is basically connecting this output with this output data bus, so that we are able to read this particular data from this particular memory cell array. Now, in this control logic, two controls are shown. One is chip select, which is active low here. Another one is WR bar. It is basically, this is write enable. In some books you will find that instead of giving this write enable and output enable together, the write and read thing is given like this. Actually, it is not write and read in that sense. This significance write. If you give 0 over here, this control logic will actually enable these tri-state buffers and will perform write operation. And if you give 1 here, the write operation will be deactivated. Instead, read operation will be activated, and these output, these tri-state buffer will then connect these output data with the output data bus. So it is designed in that way. So here WR means write and WR bar means active low write control. That is, when you are giving 0, the write functionality of this control logic or of this entire system will be activated, and when you are giving 1 over here, the write function will be deactivated. Instead, the read function will be activated. And the same thing is shown over here, only here the data buses, the input data bus and the output data bus, they are separate. That is, no feedbacking is provided here. So that is the only differences between these two diagrams. Now, if we want to design this control logic or this control logic with the aid of gates, we can actually get something like this. Here what is happening, when we want to select that particular memory cell, we have to give the signal 0 here. Why? Because chip select is active low. Fine, here we are giving 0. We are giving 0. That means this chip is selected. And suppose we want to perform the write operation. If we want to perform the write operation, we have to give 0 here. So here it becomes 1, here it becomes 1. And here it becomes 0 and here it becomes 1. So the output of this particular AND gate would be 0 because one of the inputs is 0. And here the output of this AND gate would be 1. And this one is actually goes to this input buffer. So when this is 1, this tri-state buffer will actually come down from the high resistance state and it will connect this input data bus with this input pin of the particular memory cell. So writing operation is enabled. But at the same point, since here the signal which is going to these output tri-state buffers, that is 0. That means these tri-state buffers will remain open or it will remain at high resistance state. That is, these output pins won't be connected to this particular output data bus. Now if we want to perform the read operation, we will simply change this to 1. When it becomes 1, this will become 1 and this will become 0. So output of this AND gate will now become 0 and output of this AND gate will become 1. So here it is, the 0 is going over there, 0 is going over here, means it will inactive this tri-state buffer or it will send this tri-state buffer to high resistance dome or it will disconnect this input data bus with this input pin. Instead, since here now it is getting the logic 1, it is enabling this tri-state buffer, that is, it is connecting this data pin with the output data bus like this. So in this way, read and write, these operations can take place in alternate fashion. When it is 0, the write operation is taking place. When it is 1, the read operation is taking place. So this is the whole mechanism how the data can be written or data can be retrieved from a particular memory cell or from a memory unit. Now I would like to recapitulate something. You have already know about this. When you are not dealing with digital electronics or in computer science, by K or kilo, you understand it is 1000, that is 10 to the power 3. By mega, you understand 10 to the power 6. By giga, you understand 10 to the power 9. Basically, what is mega? If you see, it is nothing but kilo whole square, that is 10 to the power 3 whole square, and it is coming down to 10 to the power 6. And what is giga? Giga is nothing but the product of kilo and mega. You see here, if you multiply kilo and mega, you will end up to get this giga. That is 3 plus 6, it is getting 9. So 10 to the power 9. Now this logic remains unaltered when it comes to computer science only. Here, kilo, mega, giga, they are all a power of 10. But here it is going to be a power of 2. And how? In computer science, while we are dealing with digital electronics, by kilobit, we mean 2 to the power 10, which comes as 1024. What is mega? Obviously kilo square, so it becomes 2 to the power 20. And what is giga? Kilo into mega, that becomes 2 to the power 30. So this is actually the mathematics that computer science or when you are dealing with bits, you need to remember this. Another thing in previous slide is address line. Here a relation is written. The address line is related with memory location through this relation. That is I, if I is the number of address lines, and M, if M is the memory location, then I must be equal to log to the base 2 M. That is exactly what is shown here. Now, this M, you must remember, this signifies the number of memory locations. Now, it might happen that one memory location, it contains one bit or maybe more than one bits. So, in both the cases, the memory location that has been used is 1. The number of memory location is 1. So the number of bits and number of memory location, they might not coincide. That you must notice very carefully. That might not coincide. One single memory location that can be pointed by using one single address bits can contain several bits. So that is one thing. And another one is that 8 bits together we call it 1 byte. And when we say one small b, we actually mean it is 1 bit. But when the 1 is followed by a capital B, that signifies byte. So if some problem is given to you, suppose you are asked that 8 capital B data, that means 8 byte data, and 8 small b data, that means 8 bit data. So now let us try to see, let us try to do a problem here. What is the problem? The problem is given that a memory module, it contains this many number of bits. So how many address lines will be required if the memory is one byte oriented, another bit oriented? Now byte oriented means one single memory location will contain 8 bit, and here total number of bits that stays in a memory module or in a memory unit is given. So how to approach this problem? Here you can do, first of all, let us see that how many number of address lines we need for this byte oriented memory. Since it is a byte oriented memory, so each location contains 8 bit or 1 byte. So how many number of locations we need for the memory to be byte oriented? Simple. We divide this total number of bits by 8. So it turns out to be 1024, and whatever comes here you always try to convert it in terms of 2 to the power something. So now 1024, it is nothing but 2 to the power 10. So here the number of address lines, now you are coming down to this formula. I is equal to log to the base 2 memory locations, and the number of memory locations that we have already calculated here is 2 to the power 10. So here comes the significance of turning it or to write it in form of 2 to the power n, since it is related through a log to the base 2. So log to the base 2, 2 to the power 10 is nothing but 10. So if the memory is byte oriented, you need 10 number of address lines to হ্যালো, আমার কথা শোনা যাচ্ছে? হ্যালো,
Yes, ma'am. Yes, ma'am.
এই কবে কখন থেকে ডিসকানেক্টেড হলাম বলো তো? হঠাৎ করে দেখছি আমি ডিসকানেক্টেড হয়ে গেছি।
মেমোরি বাইট যখন বলছিলেন তখন।
মেমোরি বাইট আছে, দাঁড়াও। স্ক্রিন শেয়ার তো আবার করতে হবে। আচ্ছা, এই স্লাইডটা কি দেখেছিলে?
Yes, ma'am. ওই প্রথমে প্রবলেমটাও দেখেছি।
প্রথমে প্রবলেমটাও দেখেছো, আর ওটার কি এক্সপ্লেনেশনটা
Yes, ma'am. Yes, ma'am. হ্যাঁ,
ছিলাম?
ছিলাম হ্যাঁ। সেকেন্ড
আচ্ছা।
মানে প্রবলেম 2 টা হবে।
প্রবলেম 2টা মানে এই 2 নম্বরটা তো বিট ওরিয়েন্টেড মেমোরি, তাই তো?
Yes, ma'am. হ্যাঁ।
ওকে। Okay. So we have seen that for byte oriented memory, the number of memory location is actually less than the total number of bits. But when this memory is bit oriented, what is happening? When the memory is bit oriented means each memory location contains one bit. So here the number of memory location and the number of bits, they are equal. So it is 8192 simply. And what is 8192 in the power of 2? That is 2 to the power 13. So here the number of address line would be log to the base 2 to the power 13, that means 13. So here naturally the number of locations is increasing than compared to the previous case, because each location is now containing only one bit. So we need more number of address line to point to particular memory cell in that particular memory unit. So in this way we can actually determine how many number of address lines we are going to need to indicate or to point all of the memory locations that we are designing, that remains in a particular memory module that we are going to design in this way. Now why is this address lines or the number of address lines important? Because based on the address lines or the number of address lines, we are going to choose a certain circuitous component that we are going to see just in a bit. So up to this, কোথাও কারোর কোনো কনফিউশন আছে? এই তিনটে স্লাইডে আমি যা যা বললাম, if there is any confusion in any place, then please tell me, I will repeat. কারোর আছে কোনো কনফিউশন? ওকে, ঠিক আছে। Okay, so we are moving on to the next section. Now what is the next section? Here we are going to deal with the internal arrangement of memory cell within a memory module. Here now we are actually going to see that how many ways are there to arrange the memory locations if we want to design a memory module. This is actually not memory cell, but it should be a memory locations. Why? You will understand that in a bit. First, let us focus on to this particular design. We have used a decoder. Suppose we have got 4 memory locations, or maybe we have got 4 memory locations. Suppose we have gotten, and in the output would be 1 bit length. That is, when one particular cell is pointed or is selected, from the output of that particular cell we can get the output of that entire system. So basically this is a bit oriented memory, each cell containing 1 bit. Now how to address or how to point to these 4 different cells? In order to do that, we have taken a help of this 2:4 decoder. And depending on the value or depending on the row value that is connected to each cell of this, we are actually pointing it, or we are going to enable that particular cell. These row actually carries the address bit. So when this is an active high decoder, so when it is 00, that means row 1 is selected, or the value in row 1 will be logic high and rest of them will be logic 0. So whenever it comes 1, this particular cell 0 is selected, or this cell 0 is pointed, and then based on that, this logic, this chip select, write, read operation, everything will be enabled for this particular cell, and either we can write data to this cell, or we can read data to this cell from this cell. So this is connected to data line, and this data line, generally two types of data lines are there. One is data line, another one is data bar line. So from each cell, you see each cell is connected to these data lines, and each cell is connected to this address line also. So this type of addressing is what we call as 1D addressing or one dimensional addressing. That means here only in one direction, only just columns. If we see this as columns, only columns, the cells are existing and is situated in one column. So only one dimension. No cell is situated in this direction as well. So this one is 1D addressing. Now the problem with this 1D addressing is that as the number of cells increases, the size of the decoder has to be increased. Suppose if there are 16 number of cells, we need maybe a 4 into 16 decoder, or if 8 number of cells, 3:8 decoder. But sometimes it is not possible to have that big sized decoder all the time. 2 to 4 decoder is very common. Maybe 3 to 8 is also very common. But what about more than that? They are not very commonly available. So to overcome this problem, from 1D addressing, 2D addressing have been adopted. Now what is the mechanism of this? Here, instead of having just the row, we have got a column also associated with each cell. That is, here the row value only determines which cell they are pointing. It is pointing to which cell, it is determined only by this one row value. But here, which cell needs to be pointed is determined by this row value as well as this column value. And this row output is coming from this decoder, a 2:4 decoder, and this column output is coming from another decoder, that is what we call as column decoder. So basically, the cells or the memory location is the intersection point of each row and each column. So each memory cell is connected to one row and to one column. So what will be the address of this particular cell, this 0th cell? It will be selected, or it will be pointed at when this row 0 value will be 1, as well as when this column 0 value will be 1. So when these two will 1, this cell will be pointed. What will be here? So here the address is given as 0, 0, 0th row and 0th column. When these two becomes activated, it will become 0, 0. So what will be the address of this particular cells? It will be 0, 0, A0, 0, A1, 0, only then the 0th row will be selected. So 0, 0 and 0, 0 here also. A1 is 0, A2 is 0. Because if only these two are 0, only then this column 0 will be selected. So the address bit would be 0, 0, 0, 0 for this cell. What about this? This one, it is connected to 0th row. So for a row address, it will be 0, 0. But here it is connected with the first column, or the column 1. So here the address bit would be 0, 0, 0, 1. This 0, 1 is coming from this column decoder. Similarly, if we want to find out the address of this particular cell, it is connected with the 0th column, but it is connected with the row 1, not row 0. So the address would be 0, 1, 0 0. So in this way 16 cells, they are addressed like this. And to locate or to point to the 16 cells, we need only two number of decoders, and each decoders are of size 2 is to 4. We do not need more than we do not need bigger size decoder than 2 to 4. So in this way we can actually mitigate or omit this problem with 1D addressing. Generally, all this memory module arrangement, they adopt this particular 2D addressing. Now, since there are rows and there are columns, we can alternatively call it as the matrix form, rows and columns. So here it reduces the size of decoder, but obviously the number of decoder is increased by 1, but still that is acceptable because the availability of small sized decoder is much more compared to this bigger sized decoder. So that is the significance of moving from 1D addressing to 2D addressing. Now if you notice carefully, each cell here is connected to uh, row line as well as column address line, and each of the cell one data line and data bar line is coming out, and here this data bar line and data line are going into this particular control block, read write etc. And this control block, we have already seen the detailed circuitry of this control block, and here it is just shown in the form of block diagram, just a block like this. And here, since each memory location contains just one memory cell, or one memory cell means from the output we are getting just one bit at a time. So this is entirely a bit oriented memory, and the final output of this system, you see there is only one data line, that is only one data line that is giving us the desired output whenever we are reading or retrieving the value from a particular memory cell. Now, what if we want to access data whose word length is more than 1? Suppose we want to deal with data which has got 4-bit length, that is 4 bit at a time. So in that case, what do we have to do? In case of 1D addressing, what do we have to do? We have to point a particular location, we have to select a particular location, but in that case, that particular location must contain 4 number of memory cells. That is, we are pointing to 4 number of memory cells at a time. So here you see, here it is only 1D addressing. So one row does not contain just one memory cell, but it contains 4 number of memory cells altogether. So whenever this particular row is getting activated, means this is 0 0 and this row is getting activated, that means all these 4 cells all together, they are being pointed at, and from each cell a data and data bar line is coming to this read write block or this control logic. So from these 4 cells we are accessing 4 bit of data at a time, and in the output we are getting D0 out, D1 out, D2 out and D3 out at a time. So 4 bit length data here we are accessing. If we want to do the same thing with 2D addressing, what do we have to do? We have to simply place more number of cells at this particular memory location. See, previously here at this intersection point, one memory location contains one memory cell and it is producing 1 bit of data. But here now, one memory location contains 0 to 7, that is 8 memory cells at a time. So when we are giving address bit 0000, this memory location is pointed at, that means all these 8 cells are being pointed at, and from these 8 cells we will get 8-bit data, here it is shown only by a single line with this symbol. This means it is not a single line data but a data bus which is 8-bit long. See, here it is same. This line is given and 8 is written. That means this is basically a data bus with having a width of or having a word length of 8-bit. And this 8-bit data bus is going to the control logic, and at the output we are getting D0 to D7, that is 8-bit long data, and that is why it is not denoted as a single line but in this way, a double-headed arrow. This represents the data bus, these two lines, and like this represents a data bus, unlike this case where it was just a single line through which we can only access 1 bit. But here now it is you see the difference in symbol. It signifies that it is more than 1 bit, and in this present case it is 8-bit long. So in this way we can organize a particular memory module and a particular memory unit. And why do we need to know how many number of address lines we need? Because based on that we are going to choose the number of decoder as well as the size of each decoder. So that is the significance of determining or finding out the number of address lines. How many address lines we are going to need, because the size of decoder and the number of decoder is going to determine or is going to take care because of that problem, because they are basically the output of these are basically giving the address lines. So that is why we need to read those. Now let us come down to the next segment. What is that? We have seen different types of memory and we have seen the internal arrangement of memory, how the address lines are designed, how 1D addressing is done, and why do we need a 2D addressing, what are the merits, demerits. We have already seen that. Now another thing which is important here is obviously the time, or how the entire operation is taking place, what exactly is the steps, or what exactly are the sequences through which the read operation and write operation takes place. Now these two are the only two operations that we need to perform regarding memories. Either we read from it or we write into it. So let us first talk about the read cycle or the read operation. So in read operation, what will be the first step? The first step, or we can alternatively call as the first sequence. First sequence, obviously we need to point out a particular memory unit. So address bits are applied. That would be the first step. Just a minute. Okay. Here it is already written. Okay. So first is address bit should be applied. Then what we have to do? The address bit which are pointing to a particular cell or a group of cell, then we have to enable those cells. So we can do that using this chip select control. We enable that. And since it is a read operation, next sequence would be data is read or retrieved from that particular memory location until and unless it is available at the data output pin. So these are the three steps. One is address bits are applied, then the memory module is enabled, and third is data read or data is retrieved. So if we see that in this particular timing diagram, What is this? This one is the address. So at this point, the address lines are getting a valid address. After that, we need to enable the particular memory cells. So the chip select here is going from 1 to 0. Why? Because it is, in this present case, it is active low. So it is falling down from 1 to 0. And next, what is happening? The data which is already present in that particular memory cell, it will come and it will become available at the output pin. So at the output, we are getting this valid data. Now there are certain things that are labeled over here. So what are these? Let us start from here. This is called TA or access time. It means after giving from it is the time difference from giving the valid address from that point until the time at which the valid data is available at the output. So from this step 1 to the final step, this is the time difference. That is what we call as the access time here, TA. What is this? This is after the chip select is enabled and from chip select to the time at which the output data or the valid output data is available at the output pin. So it is that particular time difference. It is what is denoted as TCO. So after the chip select is enabled, from there and the time needed the data to appear at the output pin, it is that much time. Now what is this particular time? It is called the hold time. Hold time means from after the address bit is taken away from here and the chip select becomes disabled. This is the time difference that is denoted as the hold time. And what is this time? This is the select to output float time. That is, it is now getting disabled, but after the chip select is disabled, up to this point of time, the output data will remain valid, or alternatively, we can say that after this time only another valid data can come to the output data pin. So that particular time is what we call as the select to output float time. It is TOF. It is denoted by that. So these are all the technical terms that comes into play when we deal with the read operation, and that is the sequence of steps through which this read operation works. Now here it is shown in the form of some block diagram. Now what are these? This delta A, this delta CS, this delta O, these are nothing but the delay associated with that particular line. Here in this case from address line to reach to this memory array. So that is the delay associated with the address line, and by delta A we are actually representing that delay as a lumped element over here, and we are denoting it as delta A. Same goes for this chip select delay, and same goes for this data output delay. These are nothing but the lumped delay associated with it, or delay associated with these lines which we are representing in the form of a lumped element. That's it. Now if we move on to the write cycle, what are the steps over here? A little bit more number of steps here needed, because here we need to give some data as well which is needed to be written. So here the first step remains the same. Obviously the address bits are needed to apply it. What is the second step? The second step would be the data that is to be written, that has to be applied at the data input pin. So that is the second step. Third step, same as here second step, that is that memory location has to be enabled. That is done through chip select. And what is the fourth step? Fourth step is we have to give this write enable signal so that the entire thing goes to the write mode. We will be able to write the data in that particular memory cell. Now, after performing this, if the CS which was enabled is now withdrawn, and after the withdrawal of this CS, if address input is changed, that is, we select a different memory location for writing data. In that case, what will happen? Again, the same process will start from sequence 2, because now it will point to a different address bit. So here basically the step 1 is taking place. That is, the address bits are applied and it is pointing now to a different memory location. So after that, if we want to write these 2, 3, 4, all these steps are going to be performed. So it has got 4 plus 1. In some books you will find that this step is considered as sequence 5, and in some books you might find that the entire sequence ends in here. Strictly speaking, the entire sequence should end after this 4th step, because this is nothing but a repetition or a cycle again that will start from 1. So basically these are the steps for write operation. Now if we want to see, if we look at the timing diagram of this particular write cycle, we will see here a valid address data bit is given. Then the chip select signal is given, which is here active low. So it is getting enabled when the signal is falling down from 1 to 0. Next, instead of data input, there is another logic input, or there is another control input in the form of write enable, which is also active low. So when it comes down from 1 to 0, only that portion of time can be spent to write the data. And the data input, here the data input, here the valid data is given. Here the data output is not shown. So here what is happening here, what is the total write time or the data write time? The data write time would be this portion, up to which this write enable is at logic low. Now you see here the dotted line is actually drawn at the midpoint of this transition. You can also draw this at here and at here. Generally, the midpoint of this transition, when in any transition, at the midpoint, if a line is drawn, that generally signifies that above this it is logic 1 and below this it is considered as logic 0. But actually that is not actually the case. A certain value from here to here, it remains logic 1, and from here to here, a very subtle range, it remains logic 0. In between there exists a region that we call as a transition region, in which region it cannot be considered as logic 0, neither it can be considered as logic 1. But for the simplicity here, just to show this particular time width, it is assumed that as if the midpoint of this transition signifies that point above which it is logic 1 considered as logic 1 and below which it is considered as logic 2. In this case it is happening. So here the dotted line is drawn like this. So throughout this enable period, or throughout the time in which this write enable is activated, the data is written. So this is the data write time, which is denoted as DW. And what is this one? This one is TDH, called as data hold time. That means even after the write enable signal is deactivated, up to this time the input data should hold its value to avoid any kind of error. It is very similar like the setup time and hold time that we have already seen at the beginning of our courses. So the same question, that is after the withdrawal of this write enable signal, it is continued to hold this data at the input to avoid any kind of error. Similarly, what is this TWR? It is the address hold time, that is after this write enable signal is deactivated, the address should hold its value up to this time in order to avoid any kind of error to appear. So this is the address hold time. And what is this one? This one is what we call as the address setup time. Address setup time means before we enable this write signal, the address value should be stable to avoid any error. So this one is the address setup time, and the total time, that is from here getting the valid address to here, this total time, this is what we call as the write cycle time, or it is denoted as WC. See here, the dotted line is starting from this midpoint and it is ending at this midpoint. So here from midpoint to midpoint, it is assumed that above this the logic is 1, below this the logic is 0. But in this case, you see the valid address, or the here it is actually starting from this point and it is ending at this point. So whatever be the point you choose, you must be careful to maintain the sequence or to maintain the same thing throughout this logic. See here, no midpoint is considered at this valid address data bit, but here the midpoints are considered. So it is always better just adopt one scheme. Either you adopt this scheme or you adopt this scheme, and accordingly you proceed. This is just your for your convenience. Now here also we can see this entire write cycle in the form of the block diagram, and in addition to this address and address lines, here a data line is inserted, and these are corresponding the delays that are associated with these lines and are represented by a lumped element and are given the name of delta I or delta A or delta CS, like that. So this is the timing requirement and the read operation, write operation in details. That is what signal has to be given after what. This is how the entire operation is done. So we have completed this organization of memory, as well as we have seen that how exactly this read operation and this write operation is taking place. Now what we are going to do, we are going to see the actual circuitry to design a particular memory cell. And here with memory cell, we will start with static RAM, or alternatively which is called as SRAM. Now we have already mentioned that SRAM can be designed using BJTs as well as using MOS. Here we are going to see both of them. Although the MOS memory, the MOS based SRAM is widely used compared to the BJT because of the reasons of low power consumption and high packing density. So here this is the circuit diagram of a single memory cell which stores just 1 bit. And we want to first write 1 in this memory cell. So let us see what exactly happening over here. Okay. So this one consists of 2 BJTs, and in BJTs with the arrowhead you can easily say that this is NPN type of transistors. So these 2 transistors, they are connected in this crisscross manner. The collector of this is going to the base of this and the collector of this is going to the base of this. In this way, these 2 transistors are connected, and here they are connected, the collectors are connected to VCC through this collector resistance RC. This basically forms the basic memory cell. Now since this is a basic memory cell, it has to be connected with data lines as well as with address lines. So here if you see this transistor, you will see that 3 emitters are coming out of one single transistor, one single BJT. Basically these are 3 emitted transistor, that it will have 1 collector, 1 base, but 3 emitters. and out of these 3 emitters of these 2 transistors, 2 are connected to the address lines. That is, here ER0 and here ER1. These emitters, they are connected to the row select line, and EC0 and EC1 here, they are connected to the column select line. And this ED0 and ED1, they are connected to data bar and data lines respectively. So this forms the basic memory cell. Now what we need to do, we either need to read from this basic memory cell or we want to write from this basic memory cell. Now which node we will look for when we are reading from or we are writing into? This and this node, that is the collector node, we will see when we are reading the value or we are reading the data or we are writing the data. That is, if we want to write 1, we will see which collector has got 1, which collector output after writing operation, which collector output has now gone to logic high. And if we want to read 1, maybe we will read from this collector terminal of these transistors. So these collector terminals are what we are going to look for when we are reading from or writing into this basic memory cell. So it is connected to data and data bar as well as to address lines. So what we need next, we need a read write logic for that. Here these 2 NPN transistors in this manner, they are forming the read or sense amplifier, and this is actually forming a write amplifier, and this one here is the control logic. So if we see this as a whole, basically this one is the basic memory cell, this is the read amplifier or has to do something with reading, obviously, because output pins are available at the connectors of these 2 transistors. This one is D out, this one is D out bar, and this bit is the write amplifier, it has to do something with writing, and this one is the control logic, and these are all the input pins that we need to provide data from outside. Okay, now before going into write operation, let us clear one more thing. Here the collector is at high voltage, it is biased to VCC, it is connected to VCC through this R. Now these emitters, they are connected to row select and column select, and when this cell is selected, that means this row will be high, that is 1, logic 1, this column will be high, that is logic 1. So here with this emitter, this is high, this is high. So generally no current can flow from here to here. So it depends whether the current will flow through this transistor, that is the transistor will be in saturation region or not. It depends on the state of the logic level of this emitter which is connected to data lines. Once it is selected, no current can flow through here, but once it is grounded, that it is not selected, doesn't matter, whatever be the value of these data lines, the current will always flow through these paths and will be grounded. So we won't be able to read or write anything in this memory cell. So to activate it, we need to give this one and this one. Now these paths are blocked, no current can flow through because the potential are high, and here the collector potential is also high, it is NPN transistor. So only there is a provision that the current can flow through this emitter or this emitter, depending on its value. So with the chip select, we can, with the correct address bit, we have selected this or we have pointed this particular basic memory cell. Now what we want to do, we want to write 1. Fine. Here you see this one is the input pin, data input pin. This is the chip select, this is the read write control. So obviously the first step, the address line that has been given, it is 1, it is 1, it is selected. Now what we have to do? Now we have to give the data. So D in is given as 1 since we want to write 1 here. So it is given 1. Now the particular module has to be enabled. C S bar is given 0 and we are going to perform the write operation, and right here is active low, we are giving 0 over here. So you see, the input of this NAND gate, all the three inputs are 1, so output will be 0. And here one of the inputs is 0, so the output will be 1. Now when this output is 1, it is directly going to the base of this transistor. So it is raising the potential of the base of this transistor, making it to conduct. So here we are getting a path from VCC to ground like this. So when we are getting the path from VCC to ground like this, what about this node? Obviously the potential of this node will then pull down to the ground because it has gotten a conducting path over here. Now when the potential is pulled down to ground at this node and this is connected to the diode in this way, so here the potential is less compared to here, obviously because it is going down, and here it is biased as 0.5. So this diode will not conduct. This diode will not conduct. Alternatively, if you see the logic over here, here 0 is given. 0 is given to base. So obviously that will send this transistor to cutoff region. It won't conduct, and when this transistor won't conduct, this entire potential is falling here. So actually this D2 will conduct now. Now when this D2 will conduct, what will happen? This basically raise the potential of this node, and this node you see is connected through the data line with the emitter of this Q1 transistor. So if the potential is raised at this node, obviously that high potential, it will be applied at this emitter. So now this third emitter is also at logic high. When this third emitter is also at logic high, this Q1 transistor actually goes to cutoff, that it won't get a path through which from VCC to ground, it won't get a path, that is it won't conduct. That means if this does not conduct, what will be the collector potential? It is not getting any path to go to the ground. So this collector potential will be almost like this VCC. It is high, it will be high, and high potential means it, in the digital terms, we can say that the logic level of this node is now raised to 1. So here we intended to write 1, D in is given 1, and here at this collector we are getting 1. So the 1 is now being stored over here. Now when this 1 is stored over here, this in turn switch on this transistor. So the VCC here, it will get a path from here to here, it will be grounded. So the potential of this node now will be dragged down or will be pulled down to 0. So this will be now at logic level low. So basically when we see that when we look for that at which node that 1 has been stored, we can see that the collector of Q1 actually follows the state of this D input, and the transistor Q2, it is storing the bar or the inversion of this data. That is, if 1 is written here, 0 will be written here. So Q1 is the transistor that actually follows the logic state of D in directly. So the 1 we have managed to store or to write 1 in this particular memory cell. Now the same thing will happen if we try to write 0. What will happen then? only here instead d in is equal to 1, it will be 0, and when it will be 0, you will see that the output of these two NAND gates will be reversed. That is, then this output will become 0, this output will become 1. And applying the same logic, you can actually see the collector here will then store 0 and the collector here will then store 1. So that I'm leaving on to you to check whether you are being able to write 0 in this manner or not. In that case also Q1 will follow the logic state of D in. That means when D in is equal to 0, you will see this node will achieve a logic low level or 0. So in this way, we can actually design the SRAM using BJTs. So we have seen the write operation over here. Another operation is left, and that is the read operation. Now we have written this 1 here and 0 here. Now suppose we want to read those 1 from the basic cell. So what we are intending to do? We are intending to get that value 1 at the data output pin. That is, we want to see whether this D out is getting 1 or not. So in this case, again we will start from here. Definitely row select and column select are 1 1. That is, the address, the correct address bit is given. It is pointed towards this particular memory cell. Now we want to perform read. So instead of giving 0 here, we are giving 1. Why? Because read here is active high. So we are giving 1, and the chip select, it is active low, we are giving 0. So as soon as we are giving 1 to this particular input pin, at the output here we are getting 0 at the output of this NOT gate, and the output of this NOT gate is connected to both these NAND gates, and it is 0 means now both the NAND gates, one of the inputs are 0. So whatever be the value of D in, it doesn't matter. Regardless of that, the output of both the NAND gates would be 1. Now if the output of both the NAND gates is 1, that means this transistor and this transistor both have got high potential at the base. So both of them will be conducting. And when both of them are conducting, this VCC is actually getting a path from here to here, from VCC to ground. A path has been established. That means the node here and here, the potential will be pulled down to ground potential. And that actually makes this diode D1 and this diode D2 as non-conducting. So now these two diodes won't conduct. So if these two diodes are not conducting, one case. Now let us come to this basic memory cell. In this basic memory cell, 1 is stored here and 0 is stored here, because in the previous cycle we have seen that we have already written 1 here and 0 here. Now 1 is stored here means what? It is connecting to the base of this transistor. So now the base potential is high. So this transistor will be conducting. But since this one is connected to the base of this transistor, that is Q1, and it is of logic low, the base potential is not high and it won't conduct. So if it does not conduct, no current can flow through this ED1. No current can flow through. But here, since this is conducting, then a certain current will flow through this transistor following this path, that is ED0, this RB, this data bar line, and this. So here, when the current is flowing, it is going here, and it is switching on this particular transistor. But this transistor, it is not getting switched on because no current is flowing through here. This transistor remains non-conducting. So in this combination, we can see now this transistor is off, this transistor is on. When this transistor is on, a ground path has been established. So the potential of this node is pulled down to the ground. So the logic level would be 0. And here, since it is not getting a path to the ground directly, the potential of this node will be pulled up to VCC, that means logic 1. So you see, this D out, at the D out pin, we are actually getting what is stored at this node. 1 is stored at this node, now it is available at the output pin D out. So we have managed to read the data 1 which is stored here from the memory cell to the output. So the read operation is now completed. Here also the D out, it follows the logic state of this transistor. Means if the logic state of this transistor is high, alternatively if the collector voltage here is high, at the output we will get logic high. So in this way, using BJT, we can design static ROM and perform write and read operation. Now if we want to read 0, which is stored here, 0, in case suppose here the bit that is stored is 0 and we want to read that, only we need to simply the same logic will be applied, but here this transistor will then be conducting and this transistor will be off then, because then here the stored value is 0, here the stored value would be 1. So the status of these two transistors will change and accordingly these two transistors will change, and at D out, in that case we will find 0. So I am leaving that to you to work out on your own and see if 0 have been stored here, whether you are being able to read that 0 from this memory cell. So we have seen the SRAM using BJT or bipolar junction transistors. Now we will see the same SRAM, but instead of using the bipolar junction transistor, now we are going to use MOS logic or MOS memory. And with MOS memories, the entire design is done using NMOS. All the MOSFETs that are being used here are NMOS, no PMOS are used. So here also at first we would like to write the logic 1. Now before that, let us see this circuit a bit detailed. This entire thing here is the basic memory cell, which consists of 1, 2, 3, 4, 5, 6 number of NMOS transistors. So that is why it is termed as 6 transistor MOS memory cells. 6 number of transistors are used. Now these two transistors, this Q3 and Q4, they are connected in such a way so that they are here acting like a simple load. You can easily replace these two transistors with a resistor because basically they are behaving like a resistor here. So this is, and since active device is used to form this load or to form this resistor, we term this as active load. The purpose of this is just to perform as a load, nothing more than that. Now here these two NMOSes, these are connected in a crisscross fashion, and from these two nodes another two transistors are connected. Basically this inner cell is connected with the data and data bar line through these two transistors, that is Q5 and Q6. So, and the gate of these two transistors, they are connected to the row decoder, and here another two transistors you will see, Q7 and Q8, the gate of these two transistors are connected with the column decoder. So by giving 1 and 1, we are basically activating this cell. Now this is the basic memory cell, and this one is the read-write sense circuit. Now let us see how we can write 1 in this particular cell. Now when we want to write 1, That means we will see these two nodes, whether it is getting low logic level or it is getting high logic level. Just like in BJT, we were looking for these two nodes. Here also we are going to consider the voltages at these two nodes. So now what is happening? We want to perform the write operation. So here in read write logic, we are given 1. Why? Because here write operation is active high. So when this is becoming 1, and what do we want to write? Suppose we want to write 1. So in the input bit, that is D input bit, we have to give 1. This is the D input bits or two input pins, that is D in and D in bar. So here we are giving 1, that means here we are giving 0. So these are the inputs that we have given. This chip select is actually not shown here in this particular design. It is not shown. So it is given here. Now this one is 1. This is NMOS device. So when the gate potential is positive, that actually switches on the transistor, and when the gate potential is negative or it is grounded, the transistor or the MOS device won't form the channel. The inversion won't take place. Right, here it is inversion mode in MOSFET. So for inverting the p-type semiconductor, the bulk, the substrate, the p-type substrate, we need to invert it to form n-type. Only through the inversion the channel will be formed, and for that inversion we need the collection of electrons over here, and that can only possible if we apply positive voltage over here. That will only induce the negative charge over here, or alternatively that will decrease the band height of this source to channel and drain to channel junction, and electrons will pour down from here to here, but I'm not going into the details of that. So basically you know that you have already studied in your MOS technology classes that what is the basic principle of an inverting MOSFET. So 1 means the channel will be formed, the transistor will be conducting, and 0 means no channel will be there and the transistor won't be able to conduct. So here 1 is given, so this transistor is on. Here we want to write 1, this transistor is also on, but since this is 0, this transistor won't be on. So what is basically happening, this VDD is getting a path through this transistor. Why this is on? Because here this gate is already connected to VCC and this is actually working as a load. This transistor is on. Why this transistor is on? It is connected to row decoder, and row decoder, the value is 1. The 1 is falling at the gate terminal of this transistor, so this is on. This one is also on. Why? Because it is connected to the column decoder output, and that is 1, so this one is also on. So it is coming here. This one is on because we intend to write the data 1, and this 1 signal is given here, so this is also on. So here, and ultimately it is grounded. So basically the data line, it is pulled down to ground, or in data line now 0 is assigned. So obviously if we see this particular point, or rather if we see this particular point, the potential of this particular point is now pulled down to 0 following this path. So this will attain a logic level low here. Okay, now this logic level, it is falling here. It is low and it is applied to the gate terminal of this transistor. That means it is getting a 0 at the gate. So this transistor is now off. As soon as this transistor is off, this VDD is not getting any path straight to ground. So the terminal or the node at this point, the potential at this node will be pulled up to high logic level. So here this terminal, this Q1 is actually giving this high or logic 1. So we tried to write or to store this one. Now it is being stored in this basic memory cell only at this node. So here this transistor follows the state of D in, the logic state of D in. In case of BJT, the transistor which is in the right side, that follows the logic state of D in. But here, the transistor which is in the left side, that is actually following the logic state of D in. So this is what is happening over here. We have managed to write this particular D in. If instead of 1 we give this as 0, the same logic will be applied, only instead of this path, maybe this will be the path then from VCC to ground. That you will check yourself, that when instead of 1 you want to write 0, what will happen and what is the mechanism of this entire circuit then. So we have managed to write 1. Next, we want to read that logic 1 from that. Now, read means we have to make the data available at the output pin, and the output pins here is situated at this node. Here it is D out, here it is D out bar. Now already logic 1 is stored in this node, and here we have seen that if this one is high, why this is getting high? Because this node's potential is pulled down to ground and this becomes low. So this one is 1 and this one is 0. It is now already stored. Here this one is 1, this one is 0. Now we want to read this one. That is, we want to make this data available at this pin. So what do we have to do? Here you see, we want to do read operation. So here instead of 1, now we are making this 0. As soon as we are making this input 0, it will simply switch off this transistor. This Q17 won't be conducting now. Now if Q17 stopped conducting, then obviously automatically this transistor and this transistor won't conduct, because through this path it is not being able to connect with the ground. So obviously these two transistors will be switched off, and these two transistors will be switched off doesn't mean whatever be the value in here, regardless of that, it won't be able to conduct or it won't be able to send the signal to ground. So these two are effectively off. So what transistor is now basically switched on? This one is switched on, this one is switched on, this one is switched on. So you see this VDD is establishing a path from this transistor to this node here, here, here. It is actually going to ground. So the potential at this node is pulled down to ground using this path, because this is on, this is on, this is on, and this is on. So it is getting a clear cut path from this VDD to this ground. As soon as the potential of this particular node is pulled down to 0, it is basically switching off this Q14. Now the gate terminal, it is getting a ground potential, almost a ground potential, if not exactly the ground potential, that falls under the logic low level. Suppose it is now getting 0.1 volt or maybe 0.01 volt, but that 0.01 volt is basically considered as logic level 0. So now this transistor is switched off. Now when this transistor is switched off, what will happen to this node? Obviously the VDD won't get a path, won't establish a path to ground following this, because this is now not active, not switched on. So the potential of this node will be pulled up to VDD or nearly VDD. So basically it will pull up to high logic level or just 1. Now here, since the terminal is high, this one is not conducting due to the fact that the voltage in this gate is low. So it will flow through this. This is on, switch on, and here it will establish a ground path. This signal which is coming from here, this actually switching on this particular terminal, this particular transistor. When this transistor is switched on, the VDD is establishing a ground path. From VDD to ground, a path has been established. So the potential of this node is basically now pulled down to ground terminal. And what is this node? This is nothing but D bar, D out bar. So here we have seen in the D out bar, we are getting the high logic level or logic 1, but in D bar we will get the 0 logic level. So in this way, we have managed to make this data which is high over here, to this output pin. So we have successfully read the stored data here from this memory cell. And here, interestingly, although the name is same, you see here also this transistor's name is given Q1, and you will say that the Q1 will follow the logic state of D in, and here also you will say that Q1 will follow the logic state of D. But here, yeah, Q1 will follow the logic state D, but here the Q1 is situated in this side, but in this case Q1 is situated in this side. So be very careful about this. Okay, one thing, yeah, right. Here this one is Q1 and here this one is Q1. So basically don't try to memorize whether Q1 or Q2 is following the logic state. Just remember that the transistor whichever in right side in case of MOS based memory, that transistor follows the logic level of the transistor which is in the left side in SRAM, which is built using MOS memory, this actually follows the logic state of D in, while the same when we are dealing with SRAM with VGT, the transistor which is situated at the right side, that follows the logic level of D in. So this is basically the static RAMs that we have seen using BJTs and using MOS transistors. Now in both the cases, I have explained only reading and writing one, but I have not explained reading and writing zeros. If you have understood this, then you will be able to perform, or you will able to form the logic in which way it is operating while we want to read 0 or write 0. Up to this সবার ক্লিয়ার হয়েছে? হ্যাঁ কি না? Yes or no?
Yes, ma'am.
ওকে, তাহলে আজকে আমি এই অবধি রাখছি। আচ্ছা, আর তোমাদের আমি বোধহয় এডিসি আর ডিএসসি এর স্লাইডগুলো পাঠাইনি, তাই কি?
No, ma'am. ADC আর DSC পাঠানো।
আচ্ছা ঠিক আছে, ওটা আমি চেষ্টা করছি এই উইকের মধ্যে পাঠিয়ে দিতে। আর মেমোরির এটা আমি কমপ্লিট করে নিয়ে একেবারে তোমাদের ওই গ্রুপ মেলে পাঠিয়ে দেবো। তো আজকের ক্লাসটা মোটামুটি বোঝা গেছে, যা পড়ানো হলো বা কিছু, কোথাও কোনো অসুবিধা
ম্যাম এই স্লাইডটা আজকে পাঠিয়ে দিলে একটু ভালো হয়। আপনি পড়ালেন এখন একটু দেখেন। হ্যাঁ ম্যাম, দেখে নিলে ভালো হয়,
দেখে নিলে ভালো হবে। আচ্ছা ঠিক আছে, তাহলে এডিসি ডিএসিটার জন্য একটু ওয়েট করো। হ্যাঁ, আমি চেষ্টা করছি আজকে রাত্রির মধ্যে এইটুকু, আজকে অন্তত যেটুকু পড়ালাম আমি সেইটুকু যাতে তোমাদের পাঠিয়ে দিতে পারি। ঠিক আছে, এডিসি ডিএসিটা তাহলে পরের উইকে পাঠাবো। ওকে, তাতে হবে তো? অসুবিধা নেই তো?
ওকে ম্যাম, হ্যাঁ হ্যাঁ
ঠিক আছে, তাহলে আমি তোমাদের পাঠিয়ে দেবো এটা। একটু ওয়েট করো, আমি তোমাদের অ্যাটেন্ডেন্সটা নিয়ে নিই। তারিখ হচ্ছে আজকে 3/12। ঠিক আছে, থ্যাংক ইউ, লিভ করতে পারো।